So what I wanted to do is kind of give you a heads up, and I've already kind of done this, so I'm going to kind of do it again. I want to emphasize the importance of this chapter, even though it doesn't seem like it's much different than stuff we've done before, perhaps. But let me give you a scenario. And I'm making this up on the spot. I don't have anything prepared when I say this, but I've heard rumors that the average weight of a tire in America is, 25 pounds. Well, it's probably heavier than that. Let's go with 35 pounds. All right. I've heard that the average weight of a tire in America is 35 pounds. All right, I'm just marking that down. Now this is the mean, the population mean. Now this is what's claimed. So what I do is I want to test this. And we're not doing this in this chapter. I'm giving you a heads up of what we will be doing after spring break. So I want to test this. And I find 50 tires. And I weigh all these tires and I get the average. Now the average for my sample, which is not mu, that would be X bar, my sample mean is 33.2 pounds. And now the question is this proof, is the fact that I got 33.2 from my sample, is that proof that this 35 pounds is incorrect? Should the true population mean be lower than that? Do we have evidence to support that idea? And here's where it intersects with the sampling distributions that we're learning about right now. Any individual tire that I pick up and weigh, on its own, that doesn't mean anything. I might pick up a tire and it weighs 28 pounds. And we could say, oh, this one's 28 pounds, but that doesn't prove anything about the mean. All right, it might be an outlier. Or one of just the lower values. Maybe I pick up another tire and it weighs 36. That doesn't give any proof that this is correct. All right, that's just one tire. And when I compare it to the mean, that doesn't necessarily mean anything. But if I took 50 tires, so I'm going to put a subscript of 50 here, and I got an average of 33.2, like what are the odds that I got 50 tires that on average are less than the mean that's claimed? So rather than comparing the individual values to a population distribution of tire weights, I'm going to instead compare my sample mean to what the sampling distribution of weights would be for that population. So I'm not using the population distribution at all. In fact, what I'm comparing this to is a sampling distribution of 50, sample size 50, all possible samples of size 50. And I want to see, is this sample out of the ordinary, unexpected, based on what we believe to be true? And that's as far as I want to go with it for today. But everything that we do with our hypothesis testing is going to be related back to a sampling distribution. And we're going to learn a little bit now. What we didn't talk about yesterday is going to help explain why we're always going to a sampling distribution. We have this lovely theorem here called the central limit theorem. And it states that sampling distributions of sample means from a random sample is approximately normal for large N, regardless of the distribution of the population, as long as the observations are independent. So if I took a random sample of individuals in a population that had a distribution that looked like this in pink, I would get an average. I could take, I get this individual, this one, a few down here, but maybe there's going to be more of them up here just because this is where it's more prevalent, a few down here, and I get however many from my sample. And then I take all those, I average it together, and I get a mean. And when I get the mean is going to be close to this mean right here. Maybe the first time I do a sample, the mean ends up right there. Maybe the second time the mean is right there. And then the third time it's right here, the fourth time right there. So no matter what, I'm going to get this mean. And the sampling distribution that's created from this is always going to be approximately normal, always, if n is large. And we'll talk about what large means. So there's the idea behind the central limit theorem. We can always create a normal distribution. And when we can create a normal distribution, we can just use our normal CDF. Okay. So that's where this all comes back to. And are there questions on this? Okay. So again, just the idea, and I am restating myself, but the mean that we get from a sample size of n equals, let's say we got a sample size of 20 here. The mean that we get from a sample of 20 from this population in pink, the mean will still hover around the same value, even if the population is not normally distributed. The mean will come back to the same value, more or less, right? And that's why the sampling distribution will lead to a normal distribution. Okay, when we're looking at a sampling distribution, the resulting distribution will always be approximately normal. The mean and standard deviation will be determined according to whether we are creating a distribution of proportions or means. So I think the purpose of that sentence is just to say we have our formulas. If it's a sampling distribution and we want the mean of sample means, then it's just going to be the same as our population mean. The standard deviation for sample means is going to be the population standard deviation divided by the square root of n. And these are not formulas you have to have memorized. These are just formulas that you need to be aware of, that they exist, and be able to find them on your AP formula sheet. Now let's say we're looking at proportions instead. The mean of a sampling distribution of sample proportions, p hat, is going to be the same as the population proportion. And the standard deviation of a sampling distribution of population of sample proportions is going to be the square root of p times 1 minus p divided by n, the square root of all that. So those formulas help us to determine what the mean of the standard deviation is going to be. All right. And then there we go. The central limit theorem, just to recap what we talked about today, guarantees that the sampling distribution will have normal distributions regardless of the population distribution. Okay. So now we're just going to go through some practice problems and talk about this a little bit. And we might not go through all these parts. All right. So in fact, I might just skip to part B for this one. And let's look at this. We've got a candy company claims that 10% of M&Ms it produces are green. Suppose that the candies are packaged at random in small bags containing about 50 M&Ms. Class of elementary school students learning about percents open several bags, counts of various various colors of the candies, and calculates the proportion that are green. I'm going to skip over to this one. So can that histogram, when we create a histogram of the proportions of green candies in all the various bags, can we model that with or approximate that with a normal model? Any thoughts on that question? Can anyone remember, what do we need to do to check that a normal model is appropriate? All right. I trust you're all out there racking your brain trying to figure this one out. And this is where what we need to do is we need to refer to the large counts condition. We want to make sure the large counts condition tells us if it's appropriate to model this with a normal distribution, a normal model, that is. So the large counts conditions, I'll just call it LC right here. And again, if this is not 100% sinking in right now, we are going to see large counts conditions so much in the next few weeks after spring break that it won't take long. It's not going to be a major stumbling block for you. The large counts condition says that the number of successes times the probability of success has to be greater than or equal to 10. But on the same thing, the number of failures, so 1 minus the probability, has to be greater than or equal to 10. So now I realize that I've got a sample size of 50 in this bag. So it's going to be 50 times the probability of success is 0.1. That equals, well, let's say it has to be greater than or equal to 10. 50 times 0.1 is 5. And we can see that that's not greater than or equal to 10. Now the other side is okay when we look at the probability of failure, and it's always going to be just one of these that you need to really worry about. So when I do 50 times 0.9 greater than or equal to 10, 50 times 0.9 is 45. So one of them's going to be no problem at all. And so that one's good. But this one we failed at. So what this means is that it's technically not appropriate to use a normal model. All right, so we can talk about the center and the standard deviation in a second, but I'm going to skip to the next question. All right, and the next question says, now suppose that this class is using bigger bags of candy with 200 M&Ms each. And again, they find everything that they were looking for. Is it appropriate to use that here? What do you guys think? Is it appropriate to use a normal model here?
Yeah, right.
It should be okay in this case. Now, again, the only thing that I'm changing is that now my sample size, oops, didn't mean to do that. My sample size is 200. So now I can do 200. The claim of 10% green is still there. So 200 times 0.1 is 20. So we're good on that. And then if I check the other one, 200 times 0.9 greater than or equal to 10, that's 180. So really, it's just the smaller percent that needs to be checked, but just for completeness, you'd want to do both. All right, so we can see that we meet the conditions. We have at least 10 successes and at least 10 failures. And that's the idea. That determines that whenever we're looking at our distribution right here, we're going to have a little bit of a tail on the left and then a nice normal distribution, and then it'll kind of flatten out onto the right. So we have something off to the left and something off to the right that's just kind of flat. But we have the entire normal distribution active. And this would be like at 0.1 right here, all the way up to, 1.0 down to 0.0. So that is, hopefully I'm not throwing things out that are confusing you. Everyone good with this idea? You can give thumbs up or something if you're feeling like that's okay. Okay, I got a couple of thumbs up. All right, I'm going to clear all this. So that's just our check to make sure that a normal model is appropriate. And so if I was to answer this question, I could answer this, in a complete sentence. Imagine this is an FRQ, and I could say it's appropriate to use the normal model because it meets the large count conditions, and then maybe I could show my numbers. All right, now the next question is use this rule, the empirical rule, or 68, 95, 99.7 rule, to show how the proportion might vary from bag to bag. So all this means is we essentially need to find the mean and the standard deviation. So the mean for a sampling distribution of proportions is going to be the same as a population proportion, which is 0.1. That's what the manufacturer claims. We're going to say that that's true. All right, in this case, we're going to say it's true. Now we get a, let me see, we need to find our standard deviation for the sampling distribution of population proportions. And that's going to be the square root of p times 1 minus p divided by n. So when I plug in numbers, it's going to be 0.1 times 0.9 divided by 200. Oops. 200 right there. And now we can just plug that in the calculator, get it figured out. All right. So it's always a good idea, always a good idea, and I've been trying to emphasize this for a long time. It's always a good idea to draw a diagram, which is a normal model. It doesn't have to look beautiful. I mean, that one's beautiful that I drew. Of course, we can see that. But this is going to be, it's going to have a mean at 0.1. That's just because the population mean is 0.1. Now, the standard deviation, first standard deviation right here, first of all, it's going to be 0.0212. So that's going to put this down at 0.788. And this is going to be up at 1.2, well, sorry, not 1 point. And I'm doing this wrong. So hopefully you can see my mistake here. That should be 0.0788. And this should be 0.1212. All right, I was off by 1 order of magnitude. That makes a big difference. Now, of course, we could subtract even more. I'm not going to try and do this in my head. So I'm just going to take the 0.0788 and minus 0.212 from there. 0.0788 minus 0.0212. If I can get that right. Oh my gosh, I was having the hardest time getting that plugged in my calculator. So that's 0.0576, and I'll subtract 0.0212 again, which means my third one, which is right at the edge of my screen, is going to be at 0.0364. Now, if I go up from there, I have 2 more standard deviations to go up. So I'm going to do my 0.1212 plus 0.0212. And then I'll add 1 more. And here's what we can say. Because we know within 3 standard deviations, and maybe I'm going too fast. Hopefully you guys are following along as just getting where my different standard deviation cutoff points are. All right. And because of the 99, the empirical rule, I could say something to this effect. We would expect 99.7, so I would even, we would expect 99.7% of, and I'll put ... so I'm not writing everything down. We would expect 99.7% of bags of 200 M&Ms, of all bags with 200 M&Ms in them, to have between 0.0364 or we might say 3.64% to 16.36% green M&Ms. So anything in that range would make sense. If we got one that was like 40% green M&Ms, that would be way beyond what we'd expect. But if it was 12%, well, that falls, there's a 99.7% chance that it's going to fall within that range that we just said. So that's not unusual to us necessarily. All right. So hopefully that's all making sense for everybody. And then how would this model change if the bags contained even more candy? What do you guys think?
Would the values keep getting closer to the mean?
Exactly. So we would expect, and kind of the same way of saying what you just said, or in a different way, the same idea in a different way is our standard deviation would get smaller and smaller, which would mean it would pull all those values closer and closer into the mean. So if we had even more, let's say there were 1,000 candies in this, we would expect our distribution to look more like this. And we would, we could calculate what that standard deviation would be, but at that point, this range going from 3.5% up to 16.5%, that would be shrunk down greatly. Okay. So there we are. I just erased all that, but if you have any questions, I can bring it back up. Okay. So this is a very closely related question, the next one. A restaurateur anticipates serving about 180 people on a Friday evening and believes that about 20% of the patrons will order the chef's steak special. How many of those meals should he plan on serving in order to be pretty sure of having enough steaks on hand to meet customer demand? Justify your answer, including an explanation of what pretty sure means to you. So what's your thought process here? So put up a little bit of a hint on the screen in case you need help kind of stimulating your thought process.
We are finding the mu with the p hat. What is that called again?
Yeah, okay, yeah, good. It's the mean of the sampling distribution of sample proportions.
Yeah, that's the word.
Okay. And I want to explain that because I keep saying it, but maybe it's worth kind of explaining what all those words mean again. This normal distribution that we're creating is a sampling distribution. But what I'm actually sampling here are proportions. And so if I had 180 patrons coming in one night, then this would be And I'm kind of jumping into the answer a little bit, but I'm not giving everything away. So I'm going to have samples of size 180. And if I did this over and over again, infinitely many times until I exhausted all possible combinations, I would get different proportions from those samples. And it would average around the population proportion, but then I would have some, there'd be some scattering around that value. So you already talked about this one. So we already kind of said this. So what would the mean of our sampling distribution be?
$36.
Oh, okay, I see. You did the 0.2 times 180. If we were doing means, that would work. We're actually going to be looking at proportions, so that makes it a little easier. So what would we use for the proportion?
Is it just 0.2?
0.2, yeah. And we could look at this, and I understand why you said means, because the question is how many of the meals. So in the end, it's coming back to means and counts and numbers, but we'll actually convert this back into numbers at the end, all right? Because we're dealing with proportions and counts to begin with. So hopefully that's okay, and that makes sense. So now we just need to figure out our standard deviation. Of course, I should have asked you what we should do next, and I just jumped ahead, but hopefully you were already thinking that. So you guys can fill in that equal sign with the answer with what you find once you've done the calculation. All right, so we got our answer to part A. It's actually a fairly straightforward normal CDF problem. The next one says, less than how much rain falls in the driest 20% of all years. What function on our calculator do we need to use for this? This is a deep cut right here. Let's see if you guys can remember. If anyone is already just rushing through and finding the answer, you can go ahead and put that here. But in the meantime, we need to remember, just to get started, I'll just put this right here. There's a particular function we need to use first of all.
Is it inverse normal?
There it is. We need to use our inverse norm. Now, the way that you can remember that, this is going back to kind of review unit 2 a little bit. If you look on the right side, we don't know this x value. That's what we're solving for. We do know the mean is 35.4, and the standard deviation is 4.2. And if we don't know everything on the right, we're going to have to use inverse norm to figure out what our percentile and therefore our z-score is going to be. We already know the percentile is 20, so I'm going to use inverse norm with 0.2. Let's write it up here. So this can be inverse norm with 0.2 as the area, and then of course the 0 and 1 model. So now I can get the z-score on this, which is negative 0.8416. And now I can just do some basic algebra to solve for the missing value. You can plug that number in when you find it. Okay, very good. We've got 31.865 inches is what we solved for. So, and notice how that's lower than the mean. Of course, that's what we'd expect if it's the driest 20% of all years. the cutoff point is about 32 inches to say if it's that or lower, that's going to be considered one of the drier years. But on average, we're getting 35.4 inches of rain. And let's go ahead now and answer the last two. And now there's a student in Ithaca for 4 years, and Y bar, now we would probably call it X bar, but the sample mean for the 4 years they're there, we're going to come up with the sampling distribution model of the sample mean. So, and I just want to run through this one a little bit quickly. I hope you guys could do this one on your own, but just to kind of wrap this up, we know that we're going to have a mean of our sampling distribution of means along with a standard deviation. So I'll just put this right here. What are these two values going to be? And I'll let you guys kind of solve those individually. I will remind you of the formula here, since you might not have that memorized. So go ahead, fill in what the answers are for our model. Okay, and to run through this real quick, very good. Those are both the correct. So let me go ahead and just write up here that we're going to have our normal model of 35.4 with a standard deviation of 2.1, which is different from our population model that we used earlier, which I did that one down here. That's 35.4 with a standard deviation of 4.2. But remember, we had to take this 4.2, which is a population standard deviation, and divide it by the square root of our sample size, which is 4. Square root of 4 is 2. So we're basically just taking 4.2 dividing by 2, and that's where we get this. Now, I want you to think about this from the perspective, like, why does this get closer? And I know we've talked about it to some degree, but if you took the absolute driest year on record in Ithaca over the last however many years they've been recording, if you took the absolute driest year and included that in your sample, you know, in the population, that would be way at the extreme, right? The absolute lowest value. But when it's included as part of a sample, even though this 1 year is particularly dry, maybe the next year was actually wetter than usual. And all of a sudden, you've brought the average to about right here. And then maybe you get another one that's about right here, and all of a sudden you've brought that up even more. So now your sample mean is getting moved up. So there's no way of getting a really, the absolute lowest value. It's always going to be moderated to some degree. Maybe you get the 4 driest years just by random chance, but still that would put you about right here instead of at the lowest value. So there's not going to be as much variation on this. And I hope that that's sinking in more and more, the more that we see this. All right, so now this is our model. Now we have a pretty straightforward question for the last one. What's the probability that those 4 years averaged less than 30 inches of rain? So what's the probability that in our sampling distribution that we end up with a sample mean of 30 or lower? All right, maybe I'll just put this. What's the probability? I'll just put probability that our random variable, or that the X bar is less than 30. And I'll just put a box right here so you guys can put that answer in whenever you find it. Now, these are definitely the kind of questions where you can overthink it and make this kind of challenging. And hopefully when you see the process for it, it's not so bad. But keep in mind, we're looking now at our sampling distribution, right? And the sampling distribution says that in a 4-year period, we would still expect there to be about 35.4 inches of rain on average. But maybe it could go down to 33.3, if I'm doing my math right. Maybe it goes down to 31.2, and even down here, one lower, it could go down to 29.1. And then somewhere in here is kind of a cutoff that says this is the 30-inch mark. So a 4-year average of 30 inches of rain would be pretty unlikely. We can already see that just from a picture. So if we draw the picture here, and I'm not worried about the stuff over here, those numbers don't matter for us. But in this picture, I can see it's already pretty unlikely. So what's the probability of getting that value or even lower than that? It's not high. So at this point, I can just do a z-score calculation. I'm going to go ahead and erase all this work over here. And I'll get rid of our previous answer there just a second. So in this particular problem, what we need to do is we need to figure out what's the z-score for that particular outcome, where I have 30-inch average over 4 years. Well, the mean would be 35.4, and the standard deviation for the sampling distribution is 2.1. It's just a basic z-score calculation, which gives me negative 5.4 over 2.1, which when I do that math, comes out to negative 2.5714, however much precision you want to put on that, because that's not our final answer. So now this 30 inches is the same as a z-score of negative 2.5714. And this is true for any normal distribution. The z-score, we can do the normal CDF. It doesn't matter this is a sampling distribution versus a population distribution. The z-score calculations and the normal calculations stay the same. So I don't have to do anything different. Now it's just going to be normal CDF going from negative infinity up to negative 2.5714 with the standardized normal model. And when I plug that into my calculator, that's where we get the 0.00506 ... which rounds to what we came up with right here. Okay. So the sampling distribution itself, the only calculations that change anything that you learned before is that we need to come up with the new model by coming up with our new mean and standard deviation. And really, it's only the standard deviation that changes. So after that, we just do exactly what we did before. So just to say it one last time, the process we did here and the process we did here are exactly the same. The only difference is we used the population model for A, we use the sampling distribution model for D. All right, I hope that makes sense for you guys. I'm going to go ahead and clear this just so we can wrap this up. Your homework is right here. It's not going to be tomorrow. It's actually going to be Monday. You're going to do your Unit 7 review. There's a small chance I will be teaching you on Monday, but I am counting on not being here next week. So anyways, that will still be just a review that's available to you. And you'll probably follow along with a video as I go through it if you choose to. There's your homework. If you have any questions on anything, please feel free to stick around. If you don't, you can have a wonderful day.